Hi, and welcome to this video by the Civil War Blue Jackets project. My name is Morgan, and I'm one of the team members who works on the machine learning and data science side of the project. And in this video, what I want to do is give you a little bit of an idea about what we're doing with all these transcriptions that you're providing us with, and also to give you a bit of intuition as to why we are asking you to draw these slightly annoying bounding boxes around each of your transcriptions. So what we'll talk about a bit today is, I guess, some technology that's quite buzzword friendly at the moment, and it's actually probably something you've heard about a lot in the news over the last maybe 4 or 5 years. We're going to be talking a bit about neural networks, artificial neural networks. We're going to be talking about something called deep learning, and we're going to be talking about a very specific kind of neural network called a convolutional neural network. Now, this all sounds very complicated, and mathematically it is quite complicated. But I'm going to try and give you a bit of intuition again as to how this actually works and how we get from an image of a piece of text to some kind of prediction, automated prediction of what that actually says. Because that's the ultimate goal of the project. We're really, really grateful that we have all of our citizen scientists like you transcribing these documents, but what we ultimately want to be able to do is to get the machines to automatically transcribe these documents. And to do that, we need them to learn how to transcribe mid to late 19th century American handwriting. So let me give you a bit of intuition how we're doing that. So you're probably quite used to seeing this. This is the interface in Zooniverse. And of course, what we're asking you to do, this is an example with heights, but what we're asking you to do is to draw a bounding box around each of these heights. So the text that's been written, you can see this one in red here at the top. This is 5 feet and 5 inches. So we're asking you to draw the bounding box around it and then of course transcribe exactly what is in there. We're asking you to transcribe it verbatim, so we're really asking you not to maybe correct any mistakes that the original author of the document might have made. And there's a good reason for this, because we want the machine to learn exactly what, or to be able to transcribe exactly what is in the original text, right? So yeah, this is what we're asking you to do. And actually what we're doing is we're getting multiple transcribers to transcribe each document, each column, each document, and then we're putting that information together, we're merging that information together to help our machines learn. So what does the data look like? If you imagine we've got, let's say, 5 people, each individually transcribing the heights for this muster roll, we actually end up with something that looks like this at the top here. And this is just a flat file database that records all that information. And what it basically says to us is that at this pixel location, so X 507 pixels from the left and Y 268 pixels from the top of the image, and with a height of 43 pixels, 23 pixels and a width of 43 pixels, this is the exact box that this person drew around the image. And because we have these coordinates, when we want to train our machine learning model, we can recreate that box exactly in the original image. It also tells us, of course, the transcription that our citizen scientist created for this, which was 301. Right? So we have a direct correspondence between a box or a small slice of the image and what the text on that image actually says, what the written text says. And this is basically what we feed into our machine learning model. It has potentially tens of thousands of these that it can learn from, potentially even hundreds of thousands of these that it can learn from, right? And we want it to learn, what does a 3 look like, what does a 0 look like, what does a 1 look like, and so on. Of course, the complexity here is that different people within that historical period would write a 3 quite differently. They're not all going to look the same. So let's see some examples of this. Here are some examples of heights. Now, obviously, because this is the mid 19th century in the United States, pretty much all of the, and they're men, pretty much all of the heights are 5 foot something. So we're going to see a lot of 5s, and this is a good example case here where you can see here the number 5, all of these start with the number 5, but you can see they're all written quite differently. There are 3 different authors here, so even the same author is writing number 5 quite differently. But as you can see, for example, this top one up here, the 5 is written very differently, so it's 5'9", So 5 is written very differently to, for example, the one below, right? So how do we get the machine to learn from these examples? Well, the first thing we do, actually, is we make some changes to the original image, right, so that it's easier for the machine to learn from. So you can see here, we've taken this part where it's just a 5, blown it up a little bit so you can see more easily. But what we've also done is we've done something called normalization, an image correction. So what we've done is we've made the background, which originally was kind of a lightish grey, we've normalized it to be white. And what we've done is we've tried to bring out more clearly the contrast in the image so that it's more obvious what is written text, what is the pen or pencil, and what is actually the paper on the background. Right, so this maximizes the amount of contrast and makes it easier for the machine to detect these differences. Now, this is an image in a computer. An image is basically just represented as numbers, right? So the larger the number, the more dark that pixel is. So if you can imagine this, let's say this image is 20 pixels by 20 pixels, you can imagine a sort of graph, or I should say an array, a matrix, like a spreadsheet, 20 columns by 20 rows, and in each of those columns and rows you would have a number that represents how dark the individual pixel is in that particular part of the image, right, in that particular cell of the image. And that's all an image is in a computer, and that's what we feed into the machine, right? So this 5 would have obviously higher numbers where the dark part, where the 5 is, and much smaller numbers down to 0 for the white for most of the background. And what we want our machine to be able to do is identify features in this image, right? And what I mean by features is kind of patterns in the image that are often representative of, for example, the number 5, or the number 7, or the number 8. Now, how do we do this? Well, we create something called filters. They're also known as kernels. And this, next to the number 5 here that we have, this kind of curly part here, this is an example of a filter, right? And this filter has been specifically designed to detect the curly tail that we often see on the end of number 5s, right? This curly tail at the bottom left-hand corner of the 5. So how do we use these filters to sort of get a feeling for what the image looks like? Well, what we do is we overlay this filter on the image, and we actually do what's called a convolution. This is why it's called a convolutional neural network. And all the convolution is it multiplies the value of each of the pixels in the original image underneath this filter here by the filter, right? So where we have a black bit on the filter, that would be a 1. Where we have a white bit, that would be a 0. And all we're doing is we're going along these different pixels and we're multiplying the value in the underlying image with the value in the filter, right? So as you can see here in this part of the image, it just so happens that there's basically no black at all, it's all white. So when we do this multiplication, we get something like 0, right? If, however, we were to then slide this filter along a little bit, as we've done here, suddenly we're starting to get some of the dark part of the filter, the ones on the filter, overlapping with black, darker parts of the underlying image, right? So we would actually get some output here if we did a convolution, maybe something like 2.7, right? And again, to give you a example, if we move this filter along again, even though there's some darker part of the image, this horizontal part of the top of the 5, even though that is underlying the filter, because it's not underlying a part of the filter that's turned on, that's black, we would still here get something like 0, right? And if you can imagine, we can move this filter around. We can keep shifting it around the image so it covers the whole image, right? And we get a matrix of numbers. And this matrix of numbers would represent how much each part of the image is like this filter. So you could imagine an extreme example here. If we got the filter down here to where the 5, the curly bit of the 5 is, it doesn't match it exactly, but it's a pretty good match for that curly part of the 5. So we would get a very large number, something maybe like 23.5, something like that, right? And so the idea is we shift this filter along, we keep moving it along the image and moving it down the image until we've covered the whole image, right? And we do this in steps so that number of calculations or convolutions that we create is smaller than the number of pixels in the original image. And if you think about it, this kind of reduces the complexity of the image down. It's making it smaller. And instead of just taking the original pixel values, what we're taking is how closely it matches this filter. Right? And so imagine we covered it here with 9 examples of the filter with some overlap. What we'd end up with afterwards is, instead of an image that was, say, 20 or 30 pixels by 20 or 30 pixels, we'd actually end up with a much smaller convolved version of the image, which in this case, in this toy example, is 3 by 3, right? And what we can see is that we have only large values where the filter very closely matches the underlying image, and we have very small values close to 0 where it doesn't match it so well. Right? And this is a general idea. Let's take an example. This is a different number 5. This has been written by a different author, right? And we could apply the same thing here, right? We apply the same filter to this image. Notice that on the bottom left-hand corner, now this filter is actually fitting this curly part of the 5 almost perfectly. So, although the numbers aren't exactly the same for these two 5s, they are almost the same. There is a clear pattern here, right? You can see if we look at the convolution for the top example and the bottom example, they're very closely matching, right? And this is the underlying idea behind convolutional neural networks, that it reveals a pattern of what 5s look like. And if you can imagine, if we applied this exact same filter to other numbers, like say the number 7, we wouldn't get the same pattern at all in the convolved image. Now, we don't have just one filter in our model, we'll have multiple filters in our model. And you can see here 4 examples of filters. In the top left, we see our original curly tail of the 5 filter. We have a filter at the top right that's maybe good at detecting horizontal lines. We have a filter on the bottom left that's good at capturing corners on images, for example. And this one on the bottom right might seem a bit mysterious to you, but this is an example of one that would be very good for identifying the main part of the number 7, right? Because it's this kind of diagonal line, quite thick diagonal line that goes along the page, and this is very representative of number 7. So if we had this filter on the bottom right, this might be a filter that's good at detecting 7s. Let's see how that works. When the filter gets to this part of the image that represents a 7, and you can imagine, further up the image, it would also match very well kind of in the middle of the image, you're going to get a very high number when you convolve this. So the pattern in the convolved version of this image is going to identify this diagonal line very strongly, right? And what we ultimately want to be able to do with this, the model ultimately wants it to be able to output something that looks like this thing below. What is this telling us? Well, obviously the machine is never going to be absolutely sure that it's the number 7, but if you can imagine, these bars represent how sure the model is that it's the number 7, and you can see that you've got a little bit of a bump for the number 1 because 1s and 7s do look in some ways kind of similar, right? But it's pretty certain in this case that it's the number 7, and this is ideally what we want our machine to output. We want it to output very high probabilities for when it's the correctly identified number. And you can see here this on the bottom on the x-axis, these are all the possible outputs for numerals that we have based on this data set of heights, right? So it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, a half, 3/4, a quarter, and so on. It's whatever unique numerals we've ever seen in our data set we want it to be able to output. And these are known as classes, these are output classes, right? So that's basically the idea. Now, one thing I should point out is you might be thinking, well, where did these filters come from? Do we as human beings manually create these filters? And the answer is no. This is the kind of magic part about the convolutional neural networks, and unfortunately I can't get into details right now of how this works. But what the machine does is it actually builds these filters itself as it's learning from the images. So as it takes these raw images, it knows what the correct answer is because you guys have been providing us with transcriptions, and like a human being, it tries to learn from those examples where it's got the right answer. So it's called the ground truth. And it tries to learn from these ground truth values, and basically it adjusts the values that represent these filters. Because again, these filters are just a kind of matrix of numbers, and it adjusts these numbers subtly every time it looks at an example image and it compares the output that it gets for that example image with the correct answer from your transcriptions. And every time it gets it wrong, it subtly adjusts these numbers so that next time it tries, it gets it a little bit more correct. Right? This distribution that comes out is a little bit more correct, where 7 would be higher in this case, probability. Right? And we run this over multiple what we call iterations or epochs, and over time the machine, like a human child learning, learns to get better at this task, better and better and better, makes fewer and fewer mistakes, and basically converges on something like optimal filters. Now actually we don't just do this process once, we do multiple convolutions in the model we're using. We actually use 5 different layers of convolutions with different filters, right? So you can imagine at the first layer, we actually have 5 different filters. So the machine has to identify 5 of these filters that make sense at this first stage. It then convolves the image. Then there's a second layer where it creates 5 totally different filters that work well at this convolved layer. And it does this in 5 different stages. And this is why it's called deep learning, because the model is deep, right? It has depth. It has lots of different layers, one after the other. Hopefully that makes some sense to you. What I'm going to tell you now a little bit is how do we get from the output from this convolutional part of the network into estimates of the probabilities of each of the characters. So this is where it gets a bit more complicated again, but you can imagine here on the top left, we have the example of an input number 5. We're going to convolve it with this filter here, right? And we see that we saw this before, we get this convolved matrix. We do the same thing for the second filter. Again, remember we would have 5 different filters that we do this with, then we'd pass it on to the next stage, it would be 5 new filters, then the next stage, then the next stage, then the next stage. But ultimately at the end, what comes out is a set of numbers that represent how well the 5 matches all these different filters as we go through the layers. And in this diagram we see here, this is what's known as the input layer. This then goes into what is known as a sort of classic neural network, known as a multi-layer perceptron or a fully connected network. And it's fully connected because, as you can see, all these are called input nodes, this input layer, each of them is connected to a number of nodes in these middle layers. These are known as hidden layers, and they're hidden because we don't see what the input basically is to that. The machine creates these links between each of the layers, right? And these links here are just numbers. And all that happens is that the numbers that come into the input layer, which comes from the convolutional part of the network, these are then multiplied by these connections. And these connections are just weights, right? So it might be, number 2, number 1.6, and number 9. In any case, it's going to go through and it's going to multiply these numbers all the way along so that eventually you get to this output layer. And the output layer should have as many nodes as there are output classes. What do I mean by output classes? I meant, here when we wanted to output high probability for the number 7, the class 7, the output classes are all the possible characters that we want to be able to detect, right? So the size of this output layer, in this case, is going to be all the numerals plus these fractions. And it's going to learn how to output high probability, in this case for the number 7. You can see it's given 0.78 probability, so number 5 in this case, it's given 0.78 probability to number 5, and very low probabilities for all the other numerals. And again, we'll go through this learning process. It takes a long time. The machine takes, in some cases, up to a day to learn this from the data. But it learns the optimal set of weights all the way through and the optimal set of filters to get this kind of high quality output most of the time. And that's basically, I know this isn't super straightforward, but that's essentially how we're doing the learning here. So I hope you found that at least kind of interesting and gave you a bit of intuition as to why we're asking you to transcribe exactly, and also why we're asking you for these pesky bounding boxes. It means that the machine can get access to and crop the exact part of the image that you were focusing on when you did your transcription and learn from what you were telling it over time. And we're actually getting some really nice performance from our model now, and the more data you give us, the better our model can get at learning this, and eventually, hopefully very soon, we'll be able to have some models that can do this automatically, and then we'll just get our human assessors, you guys, to check the output from the model sometimes to make sure it's not doing anything silly. So again, thanks for your attention. Hope that was really interesting, and thank you for all your hard work with the transcribing. We really appreciate it.